We're going to look at Decoding Starlight, but before that, let's discover a little bit more about stars. And one definition might be a luminous spherical plasma held together by its own gravity, or they're giant balls of hot gases, mostly hydrogen, some helium, and small amounts of other elements, and nuclear reactions are taking place. But what does this mean? I'm going to start off looking at what is a plasma and start that by looking at the three states of matter: solid, liquid, and gas, and how they can be interconverted. And you can pause and read the examples. And if we put plasma there, it is beyond gases. And it says to turn a gas into a plasma, you need ionization. So what actually has to happen for that plasma to be produced? So it's a very hot gas, no, it's a plasma, so hot that the atoms become ionized by losing negative electrons, so the ions are going to be positive ions. And where does the heat come from in stars? It's going to come from the nuclear reactions that take place there. And if we look more closely at the atomic molecular structure of solids, liquids, and gases, and you can pause and look at these in more detail. Solid, the particles just vibrate very slightly, they have their own shape. Liquid, more jostling, particles are slightly further apart, they take the shape of the container. And gas, the particles spread throughout the container, and particles are moving very quickly. And if we put a plasma in there, it shows that you've got the ion, the positive ion, which may actually just be a nucleus of the atom, and electrons that have been stripped off, and there will be far, far more of them than the relative amounts in that diagram. So where do you find plasmas on Earth? Lightning, an example of a plasma. In pre-2014 plasma TVs. In your homes you may have fluorescent lights, low pressure mercury vapor, but a very high electric voltage to produce the plasma. And in auroras, the northern lights or southern lights, and if you're far enough north, you'll be able to see them. Occasionally they come a little bit further south. And you may know about plasma globes. And you've got a central electrode there with, again, a very high voltage. And you can read a little bit more about there. And the QR codes, a couple of activities, but please follow all the safety precautions as you are doing those activities. And so, let's recap. It's a star, luminous spherical plasma held together by its own gravity. But what does by its own gravity mean? Perhaps everyone knows gravity. On Earth, things fall to the ground. It's a mutual attraction between all things that have mass. And of course, stars are incredibly massive. And you can pause and read through a little bit more information and look at the proportionality between force and masses. But you can look deeper into the definition of gravity, curvature of space-time. So imagine a bedsheet that's held taut by 4 people at each of the corners. Put a bowling ball on it and it will distort what was a flat, tight sheet. And that's the start of looking at gravity and relativity. And so where do stars come from? So in interstellar space, you've got dust and gas clouds, and they're going to coalesce. And as they do so, they have some gravity, and that then assists in increasing the coalescence of more material. And eventually, once you've got the right number of particles and you've got enough material in it and the temperature's right, you'll start nuclear reactions. And here's a diagram, and again, pause this one to really read what's there. But the summary is, if you start near the middle with number 1, if you're going to the left to the sun-like star, you look at the life cycle of a star with the mass of the sun, close to the mass of the sun, and what the life history of that would be going down to white dwarf. If you go to the right, more massive stars, up to 7 times the mass of our sun, or larger, and what happens to those going through the B directions, eventually getting a supernova, and a lot of that material goes back into interstellar space to produce more stars. So if we look at our nearest star, the sun, because it's closer, we can get more information from it. You can look at the structure here with the core where the nuclear reaction's taking place, the radiative zone where the energy is moving outwards, convection zone where the hotter material moves outwards, cooler material drops down to the surface, and on the surface we actually sort of see the photosphere and sometimes, usually during eclipses, the corona. And sunspots can be determined as well. And if you could look at the surface really closely, it's got a granular structure all made up of plasmas, but each one of those granules is the size of Texas, but 3-dimensional. And some sunspots there, and again you can pause to read about the 11-year solar cycle. So what do we have from the sun? We have light, heat, we have energy heading outwards, and something called the solar wind. It only goes so far, but actually the solar wind, the influence of our sun, goes way beyond Pluto, way beyond the Kuiper belt objects, KBO, and the dotted line, white dotted line, is where the solar wind will meet the interstellar medium, and the sun's influence would end. And what about the nuclear reactions? So in the sun and stars that are very like it, and 95% are similar or in the same life cycle that the sun is in, you've got the first reaction, protons, hydrogen nuclei forming deuterium, forming hydrogen 2, which then combines with another hydrogen in step 2 to make helium 3, and 2 of those join to make helium 4, which is more stable, and some more protons, which will then also go back into the reaction. And large amounts of energy and gamma rays, positrons, neutrinos also being produced at the different stages. And the sun also has magnetic fields. They're densest near the bright spots, which you can sort of see in the picture there, and they are the magnetically active regions. And there's a QR code there to look at a video. Another interesting picture where the actual light of the sun has been blocked out on the image, so you can actually see the magnetic field lines. And anywhere and in the center of the sun going to the outside, you've got a moving stream of electrons in the plasma. That's what generates a magnetic field, in the same way as an electric current also has a magnetic field around it too. And then some activities that you can do, links with the QR code, measuring the motion of a coronal mass ejection, making a spectroscope, but you do need a diffraction grating for that, and then matching magnetic activity, the third one, and active regions of the sun. And try some of those because they're interesting. Now here we've got a periodic table, and each one of the elements in the periodic table has its origin in the universe. Which ones actually come from stars? So you can have a look at the 8 items that they show you for the origin of that element, and you can see which ones actually come from stars. And an interesting one here, particularly relevant for the spectra of decoding starlight. So the elements that come from stars that we have on Earth as well, that give the colours of different fireworks. And to look at parts of the various ejections and things outside the centre of the sun, you've got the solar corona, and it's on the diagram on the right, because the outer band, then there's streamers going further out, and prominences and flares, and you can pause that to go through it in more detail. And solar flares, which are produced when tangled magnetic field lines actually break. They produce lots of radiation, and you can read other properties there as well. Coronal mass ejections, far more energetic, 10 times the amount of energy from the flare, and released by the magnetic field energy, but in larger amounts, and they're often called solar storms, and they have an effect on the Earth, on its magnetosphere, and it can, the coronal mass ejections can deform the Earth's magnetic fields, change direction of compass needles, large electrical ground currents, and protons, electrons down through the atmosphere, where you have an aurora, northern lights in the northern hemisphere, southern lights in the southern hemisphere. Solar wind, stream of charged particles released from the sun's corona, its outermost atmospheric layer. And you can pause and look at that one fairly closely as well. So, what are the types of stars? You've got a line that goes from the top left to the bottom right, main sequence stars, and over 90% of stars are main sequence stars, and if you get about 2/3 of the way down, you'll see our sun labeled, and it's a life sequence that's going down there. And pause on this one to look at what the labeling of the axes done and pick out which types of stars are cooler and dimmer and which are hotter and more luminous. To know more about stars, they're given different categories. So the main sequence stars are O, B, A, F, G, K, M. The Sun is a G-type star. There are different categories within that as well. And you'll see that as you go across and diminishing size, the temperature is decreasing, the brightness is decreasing, the lifetime for that type of star is actually increasing, and the masses, which are compared to the Sun, with the G-type being 1 because our Sun is 1 times the mass of the Sun. Now, do a little bit of research so that you can find out maybe about aging red giants, our Sun, and there's a QR code there to start some stargazing. So enjoy, and then we can go on and look at decoding starlight, the luminosity, the spectra, and the colour of stars.